Okay, so that's not what I wanted. Okay. Okay. So, welcome to this review. I have a few, I basically have as many types of example problems as I can think of. And these are all example problems from when I took the course. Most of them, actually. Some of them are from last semester. Um, and we're just going to go through each and every one of the topics that I think is really important and that'll probably be on the test. I don't know what's going to be on the test. I don't have access to that. I used to in the past. I've been able to look at the final or look at the test beforehand and know what was going to be on it, but this time that's not the case. And so I'm just basically throwing as much as I can into this video, into this review, um, and hopefully that will be beneficial to y'all who are taking the class. But just to get started, maybe there we go. Um, I just want to go over what we've been doing as the problem solving process, the process that I go through when I solve a problem, and the process that most physics professors, TAs, whoever try to tell you to get into as you approach a problem like the ones we do in physics. And that's just you breathe and relax. Like I know there's a lot of information that's happening on screen or on in the problem, but you have the tools you need to do this, and you just need to sort of sift through it, and you'll be able to do it. And the next part is to read and understand. Read the problem, make sure you understand what the problem's asking for, because if you don't understand what the problem's asking for, you don't have a general direction that you need to go to, basically. Um, and then again, after that, you draw a picture, label the stuff that's given to you. Make sure you define a coordinate system because that's important. That's probably one of the biggest mistakes a lot of students make is that they don't define a coordinate system, and so they don't have positives and negatives where they should be, and that becomes a problem in when you're especially when you're taking a test because a small mistake like that unfortunately can cost you all the points on a problem. So um, and then the next thing is to write down equations, the physics equations that you know that describe the situation. You might not need all of them, but it's helpful. As much information as you can draw from the problem is good. And as depending on what you're majoring in and what you're doing, as you start to get more practice with these kinds of problems, you'll sort of get an intuition as to what equations you will need and won't need, basically. Then number five, the fifth, and really it's the step that's probably I think is the most important, is to solve symbolically. That is to keep everything in variables and then solve, because doing it with numbers, it's easy to make mistakes, make rounding errors, and things like that. And when you solve symbolically, it's easier to check units and do things, find where you made a mistake. It's a lot easier to find, like, wait a second, there should be a mass here or something that I missed. And then after that, you just sort of look at your answer and you say, does that make sense? Like, does that physically make sense to me? Because this is a physics class. And so um, if does it make sense that, for example, if you have to figure out the force of a ping pong ball, does it make sense that that force is like 10 or 20,000 newtons? Not really. And so if you find something like that that's unusual, then you should go back and see if you made any mistakes. Of course, this is a physics class, so like sometimes the units or the numbers that we get are a little unrealistic, and like we are just sort of there are some strange problems that we do have done in this class that don't really make sense. But just keep that in mind. It's always a good um, idea to trust your intuition as to whether or not something is realistic or not. But first things first, the sort of the very basics. I wanted to start from the very beginning and sort of work up to some of the harder problems, because there are some problems on here, and we might not do all of them, but there are some problems on here that are probably way more complicated than any of the problems that have been done in this semester, at least. Um, but I just wanted to at least demonstrate how those are done because I know in the past on some of the past midterms, the professor put quite difficult problems, like problems that you had never really seen before. And I kind of wanted to emulate that and show you, like, hey, it might not be something that you haven't have seen before, but I want you to feel like the professor's not going to do that. He's not going to give you something that you can't do. So if that makes sense. And so we're going to start first with unit conversions and dimensional analysis because those two things are really important. And I don't know if he talked about it really in class, but this first example has to deal with, hold on, has to deal with just unit conversions, right? And it just asks how many kilograms of water are in 3.02 inches cubed of water. And so this one, you kind of had to like look things up. But if there's any information, extra information that you need to know, then it will be given to you in the problem. Oh, to go back. There we go. And so that's what I included, that information that you need to know here. And I hopefully you remember this problem and know how to do it. But basically, this is the process that I follow. Is I start with, this is what I'm starting with. I'm starting with 3.02 inches cubed of water, and I want to end up with kilograms, basically. That's not a very good. Okay. And I want to end up with kilograms at the end. So I start here and I look at my units. I have inches cubed, and I don't really want inches cubed because my conversion factor of density of water is in kilograms. And so, cannot see my cursor very well. And so I'm going to convert from inches to meters because that's going to be more useful to me. So I know that inches are on the top. Inches are on the top in this unit here. So I'm going to go to the bottom and put inches on the bottom, and then just put how many meters. So I want to go to meters on top, and it's 0.2 or 0. Whoops, missed another 0. 254 meters over 1 inch to convert to meters. And then from there, I am going to use my conversion factor to go to from meters. Oh, and I almost made a mistake there actually, because these are inches cubed and I want meters cubed, not inches. So this conversion factor right here, I have to cube so that my inches cubed will cancel with my inches cubed, and I'll end up with a meters cubed on top. And so that's basically that. And then I just need to use my other conversion factor. Since meters cubed is here on the bottom, I know there's 1,000 kilograms over 1 meter cubed. And then I can just do that calculation and it'll come out to be right. I'm not going to do all that because that takes a lot of time and I don't really want to pull out a calculator for that. And then this other one, this other example that I have on here that says using Newton's law of gravitation, find the units of the constant g. This is just helpful in general to help me make sure that when I solve an equation, the units are correct. And so to do that, what I'm basically looking for is what are the units of g supposed to be? What do they have to be so that this makes sense? And so I know that the force of gravity is in newtons, which is kilogram meter per second squared, like that. And if that has to equal g, which I don't know what the units of g are, and then I have two masses, so that should be kilograms squared over meters squared, like that. And so I notice that if I basically kind of solve for g here, I'll have g has to have units of, it's going to be meters cubed over seconds squared and kilograms to the -1, which if we do some, you can change that to, I can't remember the units that gives it to you in like problems and things, but those units will work out if you set them equal to newtons and things like that. But Willard, that was just a quick overview of units and things like that. Those are important to know. You should always check your units, because if you don't, then it's very likely that if you made a mistake, you won't catch it. But with unit conversions or making sure checking your units, it's very helpful to know, very helpful for me at least, to find out whether or not I made a mistake. But we'll go ahead and move on to just some more basic math stuff. Mainly, the thing I think I really want to focus on is vectors, because I know a lot of students who take this class haven't really seen those before, and it's a little more complicated. And I believe, and I'm not 100% sure, so don't quote me on this, but I believe you don't have to worry about three-dimensional vectors. So like all these things that are in parentheses, you only need that if you're in 3 dimensions, if you have a z component. And so you don't have to worry about those. But they're helpful to know. And then obviously your trigonometry, which hopefully by now you're pro at. I should also mention, I've noticed a few more people have joined. If you have any questions, or if you have anything that specifically you want me to go over, feel free to interrupt me, or just send me a message, send a message in the chat, and we can talk about it. And then I think it's useful if you're going to have something on your, I think it's useful to have this on your formula sheet or your piece of paper that you're going to use. So I wrote it down here. And we'll go ahead and move on to some of the example problems that I thought were helpful. And just sort of, these ones again are more of a refresher on how to do math and things like that. And so first we're going to look at this problem is somebody is trying to measure the width across a river. So it's trying to measure this width approximately, like that. And they're trying to do so by measuring, there's a tree, I can't really draw a tree, but there's a tree located here. And they walk this way a distance of 100 meters. And then they measure the angle here to be 36.9 degrees. Or I'll just call it theta, an angle theta, like that. And so just to solve this problem, all you have to do is use trigonometry. Since we're looking for this opposite side right here, we're gonna use, and we don't know the hypotenuse, we only know, so we have the adjacent and we're looking for the opposite, we're gonna use the tangent for that one. The tangent of our angle is gonna be equal to opposite, which is W, over adjacent, which is 100 meters. And then to get W, just do 100 meters multiplied by the tangent of the angle, and that gives us our width. And then for this one, I just wanted to review vectors really quick and how we add them together and things like that. So this one just says that we have a vector A that has a negative x component of 3.1 units, so negative 3.1 in the x hat, plus 3.17 in the y hat direction. And then what is the magnitude of A? And the magnitude of a vector, again, you just think of it as the hypotenuse of a triangle. And so this would be my x component, call it A sub x, and this would be my y component, A sub y, and you just use the Pythagorean theorem to solve that. So we would get that the magnitude of A is the square root of our 3.1 squared plus, well, I guess it's a negative 3.1, but because it's squared, it doesn't really matter. 3.17 squared. And then the other one is the direction. And so to find the direction, again, we just treat it like a triangle. And right here would be the direction or the angle. We always measure it. Well, I shouldn't say that. We usually measure it from the positive x-axis. And so, and actually in this case, our arrow, our vector, is actually not pointing this way, it would be pointing this way. And so actually the angle I'm looking for, if this is the positive x-axis here, is this angle. But to find that angle, it's usually easier to just find the angle here and then subtract 180. And so I would just do the tangent, the inverse tangent of my y component over my x component. Is, and then I would do 180 minus that. So I would do 180 minus that. And then to talk about adding vectors together really briefly. And so it says when we have a vector B that has its two components in the I and j, and just, I use x and y hat, but the I hat and j hat are the same. I hat is x and j hat is y. And so it says when a vector B is added to A, the resulting vector has no x component and a negative y component of 4.43 units. What is the value of B1 and what is the value of B2? And so for this one, I usually like to break up, just look at the components individually, because what it's telling me is that when I have a 3.10, a negative 3.10, and I add B1, which is the x component of the vector B, it should be 0. And I just solve for B1, which that's easy enough. It's just 3.1. And then for B2, I do the same thing, but now I have a positive 3.17 plus B2 is equal to 4.43. And so to solve that, all I do is just take 4.43 minus 3.17, and that's my B2. Hopefully, I don't know if that's helpful, but hopefully it is. I know vectors, especially when I took this class, this part in particular is very difficult for me, but you'll get, I guess depending on what you're studying, you'll get more practice as we do so. And so after reviewing all of that, we're finally going to move on to some of the actual physics of this class. And this one, we're going to start with kinematics, which is studying the motion of objects and being able to predict their motion based off this. And so here are just some of the definitions that we use, and then also the conversion from linear to angular. And so it's good to remember these. These will definitely help you. And then really the two constant acceleration, or the three constant acceleration kinematic equations are the same. It's just instead of using, oh, and there's a typo here, it looks like. There should not be a V here. We'll have to fix that later. But it's just the same, but instead of using linear speed and linear velocity, you use angular things instead. And so this problem is also, I think we worked on it this past semester, but it says that a daring ranch hand sitting on a tree limb wishes to drop vertically onto a horse galloping under a tree. And the speed of the horse is 9.28 meters per second. And so it asks, what is the horizontal distance between the saddle and the limb when the ranch hand makes his move? And so I'm going to draw a picture. I have my ranch hand sitting here in the tree. Let's see. And it has this distance here it gives me, which I'm going to call, we'll call it H instead. H, and then I have a horse who's over here. And he's moving at a velocity, which I'll call V naught. And I need to figure out what this distance is going to be when the ranch hand falls out of the tree. And so to do this, we're going to use kinematics. And so I'm going to describe the physical, what's happening. I'm going to write a couple of equations to describe the motion of the ranch hand and of the horse. So for the ranch hand, I'm going to write his equation as y, his position equation, y of t, is going to be equal to, I'm going to define the point where they meet right here. I'm going to call that 0. I'm going to call this positive y. And I'm going to call, we'll say moving right is positive x. So for the ranch hand, he has no initial velocity, but he has an initial height. So I have that. And then he's going to be falling in my coordinate system. He's going to be falling in the negative direction. And he's going to be falling at the acceleration of gravity, g. And that's the position equation for my ranch hand. And I'll write the position equation for the horse, which is he is starting at some negative distance d. Since I've defined positive as going to the right, he starts at some negative distance d, and then he's moving at a constant speed v naught t, like that. And so for this one, I want their positions, I want them both to be at 0 at the same time, at x equals 0 and y equals 0 at the same time. So there's a couple ways I can solve this problem. I could just set the equations equal to each other, but I think it's easier to do this instead, is to find how long, because part B asks for how long the ranch hand's in the air. So if I can find how long it takes him to fall to the ground, I can also find out how long it takes the horse to try, or how much distance the horse covers in that time. And so I have in this, from this equation right here, I get, if I want him to be at height equals 0, 0 is equal to h minus 1/2 gt squared. And solving that for t, I get that t is equal to, it's going to be 2h over g squared, like that. And now that I have that time, I'm also going to plug that into the horse's equation because I want for him to, at the same time, be at position 0. So I'm going to take that 0 is equal to, and it's going to be negative d plus v naught times the square root of 2h over g. And then I can solve that equation for d just by moving d over to the other side. and I have d is equal to v naught square root of 2h over g. And that's how to solve that problem. And then for part B, I already found that right here, because that's how long the ranch hand would be in the air. And again, if anybody has any questions, feel free to stop me and ask your question or send a message in the chat or something. Now we're going to do an example with the angular angular kinematics instead of the linear kinematics. And so with this one, it says a wheel rotates with an angular speed omega initial. It experiences a constant angular acceleration and reaches a final angular speed of omega final equals 75.9 radians per second in a time t equals 4.69. During this time, the wheel completes 37 revolutions. Find the value of A. So here, all I'm going to do is, again, I read the problem and I want to draw a picture describing it. And so I know that I have some wheel. Oh, that's terrible. And it's moving. It has some omega initial and it has some angular acceleration. And I know how long it's going to rotate, or yeah, how long it's going to rotate for. So I have a delta t, and I also have a delta theta, and that these are going to help me solve this equation. And so since I'm looking for the acceleration, I'm going to try and see if I can do that using the angular velocity equations, which are omega final equals omega initial plus alpha t, like that, right? Well, the part of the problem here is I don't have an omega initial, and so I need to solve for that somehow. I need to find another way to write omega initial. The way I'm going to do that is I'm going to look at, since it gives me a change in angle, I'm going to use that to my advantage and write a position equation that will help me solve for omega initial. So here, and also it's basically I need another equation. I have two unknowns, I need another equation. So I'm going to take my delta theta is going to be equal to my theta initial. Since we have a delta theta, I'm just going to set our theta initial to be 0 times omega initial t plus 1/2 alpha t squared, like that. And so all I do here, I want to solve for alpha, and so I'm going to try and eliminate omega initial, and probably the easiest way to do that is to take this equation here and solve for omega initial. Doing that, I get omega final. I'm going to put that there. I get omega final minus alpha t is equal to omega initial. If I plug this in for omega initial here, I get delta theta equals omega final minus alpha t times t plus 1/2 alpha t squared. And then I'll distribute, when I distribute that t there, I get delta theta equals omega final t minus, I'll have a negative alpha t squared plus half an alpha t squared, so I'll end up with a negative 1/2 alpha t squared once I combine these two terms here. And then from here, I can just solve for alpha, and I get that right here. alpha equals, it's going to be delta theta minus omega final t multiplied by 2 and divided by t squared, and there's going to be a negative also, and that will be my solution there. Let me make it nicer, like that. Are there any questions thus far? Okay. And then for this last part, I just wanted to go over briefly. So those kinematic equations only apply when we have a constant acceleration, right? We've had a problem like this in the past where we were asked to find the velocity and position. Just want to go over very briefly. Again, when we're given a position function that does not look like any of the kinematic equations that we've seen, then we can't assume that the acceleration is constant. And so for this example, if we wanted to find the different, if we wanted to find the different functions, so if we wanted to find a position function and acceleration function, we would actually have to take a derivative of this function, which is the position function, with respect to time. And so that would give us a function that looks like this. Like that. And then if we want an acceleration function, we would do it again. But I'm not going to go through all of that. Just be aware that's something that they could ask. I don't know for sure. I don't think when I took the final they asked a question like that, but it's still something that I've seen on previous tests. So just be aware that when you use kinematics, you need to be careful in making sure that the acceleration is constant. Okay, now we're going to talk about the Newton's laws of motion. Really, the main one is Newton's second law that we're going to be dealing with, which is that's what these ones are, is Newton's second law. And I'll do over statics really is exactly the same thing. It's just typically there's a lot more equations and a lot more solving that has to go on. And we'll go over a couple different problems. This one is probably the one we'll spend a lot of time on. But we'll just jump into some of the questions that we have. So, for example, in a block on an incline like this. So, for a problem like this, what we are looking for, the main thing is that instead of defining our coordinate system like we normally would like this, what we're going to do instead is shift it so that the x direction is parallel to the slope and the y direction is perpendicular to our slope here. And this question asks, what's the magnitude of force F? I think there also asks a couple other questions about work, but we're just going to find the magnitude of this force here. And to start, when I draw my picture, I mean, if they give me a picture, I usually just like to use the picture they gave me, but draw a picture similar to this, basically exact same thing. You don't necessarily need to include this, just something that represents the block, that it's on an incline. And then the other thing is to draw a free body diagram, where if this is the center of mass, I have to look at all the forces that are acting there. In this case, we're going to assume that all of them are acting to the center of mass. And so here we have force of gravity, which in my coordinate system will have a y component and an x component. I'll call that the weight in the y direction, the weight in the x direction. I'll have the normal force, which is dotted, which like that, the normal force. And I'm also going to have friction which is going this way, and that's going to be kinetic friction. So I'll call that little f sub k. And then I write with these problems, I like to write Newton's second law in both directions. So the sum of the forces in the x direction is going to be equal to since the acceleration in this case, even though it's not explicitly stated, we can assume that all the acceleration is in this direction, the x direction. So the sum of the forces is going to be equal to the mass of the block, which they call capital M, so I will also call it capital M, times the acceleration. And then I look at all the forces that are in the x direction. I have the force, and I forgot to break this guy up into x and y components. And this guy is going to be my theta is going to be right there. And so I'm going to have the force of F in the x direction. So maybe that was a poor choice of notation, but we'll stick with it. Minus the force of friction minus the weight in the x direction. And that all has to equal mass times acceleration. And then in the y direction, I have the sum of the forces. Since in this case, my y direction is perpendicular, there's no acceleration happening in that direction. That's just going to be 0. And I have the normal force in the positive direction minus the force that's being applied in the y direction, and minus the weight in the y direction, equal to 0. And so from here, I'm trying to find the magnitude of force F, which none of these equations so far can really tell me anything about that. So what I'm going to do is write each of the components in terms of their magnitudes. And so for Fx, that's going to be F cosine theta. And for Fy, it'll be F sine theta. For the weight in the x direction, that's going to be mg, since that's the magnitude of the force of gravity in this case, times in this case, since my angle is up here, theta, I'm going to use sine of theta instead. Sine theta. And then the other thing I have to worry about are actually, those are the only things that I have to worry about for now, but we will see that there's other stuff that we need to take care of. So rewriting my equations, and I'll rewrite them over here, I get the normal force minus the force in the y direction, which is F sine theta, minus mg, and this one is in the y direction, so it'll be cosine theta is equal to 0. And then here, remember that the force of friction is going to be equal to the normal force times mu, in this case mu sub k, because we're looking at kinetic friction. So what I have to do here is F sub x is F cosine theta minus n times mu sub k minus mg sine theta. And that is equal to the mass and acceleration of my block. So now that I'm here, I can see that I'm trying to solve for F, but I don't know what the normal force is. Everything else I can calculate, or I'm given values for, and so this becomes a system of 2 equations and 2 unknowns. So since I'm trying to solve for F, I'm going to eliminate the variable n by solving for it first using this first equation here. And that will give me that n is equal to F sine theta plus mg cosine theta. And I'll substitute that in for my n up here, which is, it is a lot. It's pretty messy, but the algebra isn't too bad. Just need to make sure to keep track of anything, of everything. So let me erase that. Doing that gives me, oh, didn't want that. Doing that gives me f cosine theta minus n, or not n, I'm replacing n, so not n, minus, this is going to be f sine theta plus m cosine theta multiplied by mu sub k minus mg sine theta, which I mixed up. I didn't do capital MG. That's okay. I'll switch back to lowercase, I suppose, like that. And to solve an equation like this, I will distribute my mu sub k to both these, move anything that does not have an f over, and then factor out my f, and then divide by what's left over. And so doing so, I will get a final solution of MA, so F, I should say F equals magnitude of F equals MA, and I'll get a plus mg sine theta minus mu k mg cos theta, which I won't be able to fit. And all of that divided by will be cosine theta minus mu k sine theta. And that would be my symbolic solution. And I can always check my units here. I'm looking for something in newtons. This is a mass times its acceleration, which will give me something in newtons. This is also a mass times its acceleration, will give me something in units. This one is a mu k times mass times acceleration, and the mu k's, the coefficients, don't have any units on them, and so that will give me newtons. And then this down here is unitless, and so I know that at least my units are right, which means I probably didn't make an algebra error. It's possible that I did. Maybe I missed a negative or a positive, but we'll move on from there. This is a problem that I don't think we've really done a whole lot of this class, at least not in this semester. It says we have a loaded car. A roller coaster has a mass of 320 kilograms. It goes over the top hill with a speed of v equals 21.4 meters per second. The radius of curvature r of the hill is 15.4 meters. What is the force that the track must exert on the car? It's positive is up. So it's asking me what right here, right? So for a roller coaster, usually the car is stuck to the track, and it's asking me basically what is the force that the track must exert on the car to keep it from moving up. And so to do this, it says it gives us a radius of curvature. So by giving us a radius of curvature, we can approximate the acceleration that we need. Just like with uniform circular motion, we can approximate the acceleration we need, which is a centripetal is equal to v squared over r. And so in order for, and I also should keep an eye, moving a little bit too far ahead, but so there's a force that the tracks are exerting on the car, but there's also the force of gravity, right? I'll draw that a little bit over here. There's the force of gravity pushing down. And so I need to keep that in mind. But I know now that the sum of the forces in each direction. Since it's moving along this curve, it has to equal the mass times the acceleration, the centripetal acceleration, which in this case is v squared over r. And so the two forces, oh, and it says positive is up, so this should be a negative v squared over r, because the acceleration is pointing downwards in this case. And so, and then I just have the force of the track plus mg has to equal m times v squared over r. And I can solve that pretty easily just by moving over that mg. M times v squared over r. And actually, I'm gonna factor out that m and do it like this: v squared over r minus g. Now, in this case, I did assume that the force is pushing down, but it could just as well be that the force is actually pushing up. So if my answer comes out negative, then I know, or if it comes out, it should come out, if it comes out positive, then I know that, oh, it's because I messed up my signs, actually. I assumed that downward was positive when these should actually be negative. Let me fix that. So since I said that, since it tells me that positive is up, these should actually be negative if I'm assuming that they are in the downward direction. And so this will actually be a plus here. Well, all my negatives end up canceling out anyway, so it doesn't really matter. Yeah, all my negatives end up canceling out anyway, so it doesn't really matter at the end of the day. But since I defined up as positive, if I end up, I should, if I get up a positive number, then it'll tell me that the force of the track is actually pushing up. Otherwise, it's pushing down. That there, and then we'll move on. Okay, for this one, I don't know if we did a problem like this in this semester, but we have a pulley, and they're connected with an ideal string, but the pulley rotates with no friction, but it has significant mass. And so what that means is that there are forces being exerted on that pulley, and we have to take those forces into account. And there are actually a couple ways we can go about this problem. But in this case, we're going to use torque and Newton's second law to find what the final speed of the masses will be, because since they're all connected, their speeds will actually all be the same. And so first, I'm going to draw a diagram here. I have this tension 1, we'll call it, and this is capital M times G. And here I have tension 2 times mg, like that. And I also have here, acting on this pulley, I will have this will be tension 2, and this will be tension 1. And for positive, what I'm going to do is define whatever the direction I think is going to be, that the system is going to move. I'm going to define that as positive. So in this case, it's going to be going around like this, right? And so in this case, for my mass 1, I'm going to write Newton's second law for the capital M mass. And so the sum of the forces on capital M are going to be equal to, since I defined the downward direction in this case is positive, I'm going to say that mg, capital MG, is positive. going to say capital mg is in the positive, and I'm going to subtract tension 1 off of that. And here, then I'll move on to the second mass, and that's going to be equal to the mass times the acceleration, and that's going to be equal to, in this case, mg is negative, so we'll do tension 2 minus lowercase m times g. This should be a capital M. Is equal to mass times acceleration. And then finally, I have to worry about the pulley, but there's a problem in that I can't really quantify, I don't really know what to do about the force that's keeping this pulley up. So instead, what I'm going to do is take the torque exerted on the pulley about its center. In doing so, since sum of the torques, that's time on the pulley, is going to be equal to, and this one is going to be, since my tension 1 is in the positive direction, it'll be the torque on due to tension 1 minus the torque due to tension 2. And that's going to equal the moment of inertia of my pulley times its angular acceleration. Okay. And these are about as simplified as I can make them, but I can simplify this more if I know, since I can look up, or if I have written down that the moment of inertia for a pulley, this one says a uniform disk of radius r, that the moment of inertia of my pulley is going to be the mass times the radius squared divided by 2. And if I know, since the torque is going to be the radius times the force applied times the sine of the angle, which in this case, since these forces are acting tangential to the pulley, that's just going to be sine of theta is just going to be 1, so it's just going to be r times f. And so I can write my torques differently, and I get that torque tension 1 is just going to be tension 1 times r minus tension 2 times r is equal to, my moment of inertia is mr squared, and I'll put the 1/2 right here, times by alpha. I can eliminate an r right here, and one r goes away, and I end up with an equation, tension 1 minus tension 2 is equal to 1/2 mr times alpha. And it should be, well, I should have distinguished that. It should be m mass of the pulley times alpha, or time, yeah, mass pulley. This should be mass pulley, and this one should be mass pulley as well, like that. Now notice one other thing is with r times a alpha, I know that r multiplied by alpha is actually going to be the same as the tangential acceleration, which in this case is going to also be the same as this acceleration and this acceleration. So I can even write that tension 1 minus tension 2 is equal to 1/2 mass pulley times by the acceleration, like that. And then instead of having a system of equations with 2 unknowns, I have a system of 3 equations and 3 unknowns. So in this case, what I would have to do is I need to solve for tension 1 and for tension 2. So tension 1 will be equal to, oh, go back. Tension 1 will be equal to m, capital MA minus capital mg, and oh, actually, it's backwards. This is backwards. It should be ma minus mg, like this. Capital Ma minus capital Mg. That, and then tangent 2 is equal to, and this one is going to be lowercase mg plus ma, like that. And then I can substitute those into my equation down here, and I get that ma minus mg minus, let's say, mg minus ma, gotta erase some stuff here, is going to be equal to 1/2 1/2 mp times a, like that. So once I have that, I can solve for the acceleration, because I'm going to need the acceleration if I want to find the speed of the system at the end of this height h. And that will give me a is equal to, and I get, let's see, get negative mg plus ma, like this, or not ma, I think it's lowercase mg. Yep. Divided by, that's going to be 1/2 mp times by, or plus m plus capital M. Like that. I get that for my acceleration, and then I can plug that into my kinematic equation. The v final squared is equal to acceleration, which like that, 2 times acceleration, times by my delta, my change in position. So in this case, this will be the height h that's given me, and I can solve that to get that like that. I plug this into here and then take the square root, and that will give me my answer, which if I write that all out, the final is equal to square root negative, and I think I might have missed negative or had an extra negative somewhere, because that's, oh, I think that's what happened, because I don't think there should be an extra negative there, but we will see. This should be the answer that you get, is h times mg plus times divided times 2. That's divided by 1 mp plus m plus capital. And that would be our final solution. And there is another way to do this. We can actually do this with energy conservation, but we'll talk about that later when I get to it. Then for this one is statics. So for statics, we always assume, since nothing is moving, we always assume that the sum of the forces in all directions is 0, and the sum of the torques in all directions is 0. So keep that in mind. So it says the figure shows a cross member of a bridge lying in the XY plane of the page. The mass of the member is M equals 129 kilograms, and its center of mass is at geometrical center. Two forces, F and R, are acting at O and A, and it gives us an angle, and it tells us the magnitude of this component, R sub y, is going to be equal to 2 plus 2 times mg. And so I think it's giving us a coordinate system to deal with where this is positive y and this is positive x. And so for this type of problem, and actually I believe the full homework problem asks us to solve for these forces as well because we don't know what they are. But I'm just going to focus on solving for Rx in this case. So I'm going to draw the other forces that I don't have labeled. This one, which is like that. And then I'm going to go ahead, since I am trying to find the force here at the bottom, I'm going to change color. So I'm trying to find this force here at the bottom, this R force. What I'm going to do is use torque and put my axis of rotation up here, because then my axis of rotation is up here. There's no torque due to these forces here. And so by doing that, it makes it easier for me to work with, to write an equation that helps me. So if I write the sum of the torques about that point is equal to, and about this point, I have this is going to exert a torque, this is going to exert a torque, this R sub y, and this R sub x are going to exert a torque. And so since I'm going to define the torque vector that's positive to be the one that's pointing out of the page. And I wish I could review the right-hand rule with y'all, but I don't know how helpful that would be just over Zoom. Hopefully you remember it, but I'm going to say that the torque vector that points out of the page is going to be the positive one, and the ones that point into the page are negative. So in this case, I have a torque due to gravity, and that's going to be positive. And then also my torque due to the force Rx is going to be positive, and the torque due to Ry is going to be negative. And so now, and that all equals 0. So now the only thing I'm left with, that I'm tasked with now, is really just finding the magnitudes of those torques. And the way I like to do it is this is my axis of rotation, this point right here. I draw what's called a line of action. Each of the forces that I'm worried about or that I know exert a torque, I'm going to draw what's called a line of action. And it's just basically continuing the line of the force. So if this is my force mg here, I'm going to extend that line on forever. And I'm going to do the same with this force, Rx, and this force, Ry. I'm going to go draw from the axis of rotation. I'm going to draw a line that goes from my axis of rotation to the line of action of the force. So for this one, it's our mg. And so I want this distance, the shortest distance right here. So I know this angle is also theta, and I know this hypotenuse is L over 2. I'm going to use that the torque due to gravity is going to be equal to R, which is going to be, in this case, since that's the adjacent side, it's going to be L over 2 cosine theta times the force itself, which is mg, like that. Then for the torque due to R sub x, I'm going to go from my axis of rotation to the line of action of the force, which is this whole length right here. And so that whole length is going to be the sine of that angle times the full length. So it's going to be equal to L sine of our angle multiplied by R sub x, which we don't know. That's what we're looking for, right? And the torque due to R sub y is going to be, and it's actually just going to be, since they're an x and y component, I know that they are going to be, instead of sine, it's going to be cosine in this case. Yeah, and so I'll have L cosine. And since I know that R sub y is plus mg, I'm going to put plus 2mg. I'm going to put 2mg in front. Or, yeah, 2mg. Like that. And then I just put those back into my equation. And I get an equation that looks like L over 2 cosine theta times mg plus L sine theta times R sub x, which I don't know, and minus L cos theta times 2mg. That all equal 0, and I can solve for R sub x. Doing that gives me, and actually all my lengths will cancel out. So solving for the force Rx will give me cosine, this side gives me cosine, I'm gonna, yeah, so cosine theta times 2mg minus 1/2 cosine theta mg all over sine of theta. And I could simplify that more, but I will leave it like that. And then once we know this force, it's actually pretty easy to solve for the other forces, these F and X and Fy, because Newton's second law, this one, is still true. And so I know that the force of, since we're in static equilibrium, I know that the force of Rx has to be equal and opposite to the force of Fx, because if it wasn't, then the ladder or this bearing would move, this cross member. And so it's not too bad from there. You just use Newton's second law to solve for the other two if the problem were to ask for it, which I don't know if you will have problems like this, but I think it's helpful to practice or know how we can use what we've applied to these problems. Okay, so we're going to be done with Newton's second law for a bit, and we're going to work on work and energy. I did include, I do not know if you will need to know this because he didn't really teach it or test it at all, but I did include the gravitational potential energy using Newton's Newton's law of gravitation, this one here. And I don't know if you'll need to know that, but I think it might be helpful. We won't I don't think we'll really do a whole lot with that. I think at the very end, if I decide I want to, we'll talk about what it means and what it can be used for. But for the most part, we'll just be using this one, which is that the potential energy near Earth's surface is mgh. Okay, and also I included this one for the spring. That's good to know. So this one is from the homework again. We have your friend gets a flat tire driving up a ramp with a 35-degree slope right here. And he lets go of the spare and it rolls down the hill, and then it hits his sister stop car. And so this one we'll model it as a cylindrical cell. shell with mass m and radius r. So we have this thing here, and it's going to go a distance d, and it's going to have some final velocity that we're looking for. It has a radius r and a mass. So for this one, we'll use conservation of energy. When we do that is we just look at what the potential energy is, and we define where our potential energy is going to be 0. And so at the bottom, when the tire hits the car, we're going to define this as our UG equal to 0. The thing about potentials is it's all relative to some point. You can define a potential anywhere, and it could be different, relatively speaking. And so here we're just going to say our potential is 0 there. And so initially, this height, I need this height, whatever this height is. That's my potential energy, my initial energy is going to be mgh. In this case, h is going to be the distance times the sine of the angle. And then my energy final, in this case, since it's rolling, I'm going to have both rotational kinetic energy and translational kinetic energy. So for my rotational, I know that's 1/2 mass of the tire times its final velocity squared, which I'll just call v because we don't have an initial velocity. And plus, it's going to be 1/2 the moment of inertia times omega squared, like that. But I know from my textbook that the moment of inertia for a cylindrical shell is going to be equal to just the mass times the radius squared, like that. And so if I plug that in here, I get this is 1/2 m times r squared times omega squared. Now I kind of have a problem here because I don't know what omega is. I don't know what the final angular velocity is, but I do know that from my kinematics that v is just equal to r times omega. Okay, my radius times the angular velocity, my tangential speed is equal to r times omega. And doing that, I can rewrite r squared omega squared as another v squared. And when I do that, I get energy final is equal to 1/2 mv squared plus 1/2 mv squared. And then if I set those two equations equal to each other, I get mg d sine theta. If I combine these two terms, I get mv squared. So that cancels with that m, and then I end up with solving for v final. I get v is equal to the square root of g d sine theta. And I am done. Okay, and then this one, this is a problem. I think I never saw the problem that you guys had on your midterm, but I think it's similar to the one that was on your midterm. And hopefully doing a problem like this, and I've gotten quite a few questions about it, but doing a problem like this, we can sort of see how it works and do it. And this one, we're actually going to use the work kinetic energy theorem to solve. And so the work kinetic energy theorem says that the net work done on an object is going to be equal to the change in kinetic energy of that object. So we'll go ahead and read the problem. It says a crate of mass m equals 8 equals that. I'm not going to say the numbers. Is placed on a rough incline. Near the base of the incline is a spring with a spring constant that we know. The mass is pressed against the spring so that the spring is compressed a distance x from its relaxed length and then released. The mass is now connected to the spring, so when the spring reaches its relaxed length, it does not pull back on the mass. Instead, the mass slides freely up the slope before coming to a stop. The total distance d, the mass moves from the compressed point to the final point. So this not, it's going to move some distance d like this. Is that, and we know the coefficient of kinetic friction is some. So if I look, what I'm going to use is the work kinetic energy theorem. So if you remember, work is going to be equal to force, the force vector dotted with the displacement vector, like that. So I'm looking basically at all the forces that are acting in the direction of motion. So here I have a spring that's acting, the force of the spring is acting in the direction of motion. As it turns out, that the work done by this spring will be equal to, so the work, so the sum, what I'm looking for is the sum of the work. That's the net work done on the object. So the work done by the spring is going to be, it's going to be the work of the spring. All my forces are, there's a force of the spring, there's the force of gravity, and there's the force of friction that's going to push back that way. So it's going to be the work, since the spring is acting in the same direction as the direction of motion, I know that that's positive work being done. For the for friction, it's going to be against. So I know there's going to be negative work being done by friction. And for gravity, I know that's also going to be against, since gravity, the component of gravity that's acting here in the direction that's parallel to the direction of motion is this way. So I'm going to take the force of gravity, and specifically the force of gravity in the x direction, because that's the part that that's the part that's in the same direction as, or opposite to the direction of motion. So now I just need to calculate that. The work done by a spring, it happens to be 1/2 kx squared. And the way that we can derive that, there's a couple ways you can derive it. The way I like to, and makes the most sense to me, is I remember that force is equal to the negative derivative of potential energy. And so if I want to find the, basically it's amount, I guess it's more, what is the amount of energy that, maybe that's not the best way to do it. I think the best way to do it is probably just to say that when we're talking about work, it's like what we're taking, what energy are we putting into, and what energy are we taking out of the system, is the way I like to think about it. And so the spring is putting energy into the system, and it has a potential energy of 1/2 kx squared. So it's putting that energy into the block. So I know that the work done by the spring is going to be 1/2 kx squared, which is the potential energy stored in that block right now. And I'm trying to solve for this x here. That's what I'm trying to find, is how far the spring was compressed. So I have that, and then the work done by friction is going to be equal to the force of friction times the distance d that I travel, right? Because that's how long it's going to act. And then for gravity, I just want the x component of gravity. So if I draw, if this is my gravity vector, I want the x component, the component that's acting in the direction of motion. So that would be the sine of that angle. So it's going to be mg sine theta. And then what I want is it's the same distance, actually, distance d, right there, because that's how long it's acting. That's this distance, force times distance. So this is, or times displacement. So this is the same distance there. And that is there, and I know, so since I start at rest and I end at rest, the change in kinetic energy in this case is actually going to be 0. Right? It's going to be equal to 0. And so that's going to be equal to 0. And then I can solve for x squared, for this x here. And I get that x is equal to, and I get 2 times D times, oh, I don't know what the force of friction is. So I have to calculate that, but I can calculate that because I know that the sum of the forces in the y direction are equal to 0. And so since the only forces acting are the normal force in the positive direction and the y component of gravity, I know that the force of gravity, or I know that this is going to be equal to mg cosine theta, like that. So let me do that again. So substituting that in for F is going to be mu sub k times n. So I'm going to have mu sub k, or just, yeah, that tells me mu sub k. Mu sub k times mg cosine theta. So then solving for it, I get, I'll get 2 times, that's going to be, we'll factor out some stuff. We'll do 2, and it's going to be, I can factor out my m, my g, and my d times, and this is going to be sine theta plus mu sub k cosine theta divided by k, and then I got to take the square root. And that is my solution for this problem. Hopefully that's helpful. I know he didn't really talk about springs that much in class, and there was a question like this that threw a lot of people off. And you should make that k better. Like that. Okay. I guess I skipped example 10 anyway. Okay, so for this one, this is actually the same problem that we did earlier, but we're going to do it an easier way. The easier way to do this problem is to use energy in this case. And so if I look at the initial, if I take this as my system, and I know I can look at the energies in the system, my initial energy, since it starts at rest, is just going to be equal to, the only thing that has energy in the system is the mass, or I should define my potential equal to 0. We'll say potential equals 0 is here. I guess it's more right here where the center of mass is. So that's my potential equal to 0. And so right now, the only thing that has potential energy is my my mass, my big mass, and it has a potential energy of mgh. So I get mgh is equal to my final energy. Everything is going to be moving, and so everything is going to have kinetic energy. My big mass will have a kinetic energy, b squared. My small mass will have kinetic energy. My pulley will have rotational kinetic energy. I guess I should make that more clear. We'll make this a cap like that. And I also have my little mass m will have potential energy. And technically speaking, the pulley itself will have potential energy at the beginning and end, but if I were to add that to both sides, they would just cancel each other out. And so I'm not going to worry about including that in my problem. Plus mg plus mg, little mgh, like that. And I can solve this problem for, well, I guess this shouldn't be here yet. I got a little too ahead of myself here. This should just be I omega squared. I omega squared. Like that. And so, again, I can use the fact that I know from my textbook or wherever that the moment of inertia is going to be the mass of the pulley times the radius squared divided by 2. If I get that, I get mgh equals 1/2 mv squared plus 1/2 mv squared plus 1/2. Actually, I'm going to go ahead and take that, multiply that through, and get 1/4 m, and that's going to be r squared omega squared plus m lowercase m h. Again, I can rewrite this r squared omega squared as v squared, because that will be the tangential speed of the edge of this disk here, which is going to be the same speed as everything at the end. And then solving for v squared, I get, let's see, get m minus m times, yeah, I must have made a mistake on the last one because there's no negative here, or gh, or times gh, all of that divided by, and this is going to be 1/2 capital M plus 1/2 lowercase m plus 1/4 mass pulley. And then I just need to take the square root to get. And that was almost the same as the last one. I must have made a mistake on that one because I had an extra negative sign. And so, but this is the, well, should be the solution that you get from even using the other method, but this one is a little bit easier. So just keep in mind that there are multiple ways to solve the same problem, and some are definitely easier than others. And it's a lot, as I just showed, it's a lot easier to make a mistake using some methods than other methods. Okay, so we'll go ahead and move on to momentum. And so for this, for momentum, we have both linear and angular, and we also have this thing for center of mass. We have elastic and inelastic collisions. I don't know if there will be any problems with center of mass, but I'm not really going to go over any center of mass problems, just because the ones that I don't know, the questions that I've gotten with center of mass are usually a little more complicated, and I don't think that they would put anything like that on the final, because we never really did anything like that. But we'll start with an example where we have a ball that's dropped from a height h, and then it bounces off the ground originally to about 88.5% of the original height. Ask us to ask what is the change of the ball the momentum change of the ball during its collision with the floor. This one, since we said believe these upward is positive, yep. So originally the momentum is going to be negative mv. We'll use v1, and that's not that. Should use negative. We should use v. Call this one v1. Call this one v2, and call this one v final, and then we'll call this one v naught. So negative vm. At the very bottom here, we'll have a momentum of negative 1, and that's going to change to a, oh, I didn't mean to do that. There we go. Hold on, mouse, there we go. Negative V1, and then it's going to change to a positive V2, and so we end up with we do our change in momentum, mv2 minus a negative mv1, and so we just have m2 plus mv1 in magnitude. Only problem is we don't know what either of those velocities are, and so the way we can do that is, even though in this case we know specifically that it is not an perfectly elastic collision, because this obviously has less energy when it comes back up, because it doesn't come back up to the same height like that. It only goes up to part of the height. And so we can't quite use conservation of kinetic energy, but what we can do is use conservation of energy in, we'll say, let's use a different color, for right before it hits the ground and after it hits the ground, like that. So doing that, we can say that my energy naught is going to be equal to my energy at the bottom, energy 1. And so I have an mgh equals 1/2 m, since I'm going to define this as potential equal to 0, and 1/2 m v1 squared. My masses cancel out, and I end up with v1 is equal to the square root of 2gh. I can do the same with this, except now it's going to be mgh times 0.885 is equal to 1/2 mv2 squared. And then solving for that, I get a very similar answer, just mv2 equal to the square root of, it's going to be 2 times 0.885 gh. Then I can take these and I just plug them in here, and then that will give you my answer for part A. For part B, all I have to do is look at, since it sticks to the floor, my change in momentum is just going to be my I guess, my final minus initial. And so my final momentum, since it sticks to the floor, is going to be just just going to be 0. And then I'm going to minus my negative initial momentum, which is just this. And so I just need to plug in this here, and that gives me my answer. Okay, and then for this one is kind of a weird problem, and we didn't do anything like this, but I think it's kind of help us to understand how we can use angular velocity to solve certain problems, or angular momentum to solve certain problems, other than things like when I think we had a problem where it was a rotating thing on a bar where the moment of inertia changed, like that. This one is a little different, and we're trying to find, for this one, what we're going to focus on is just trying to find the wheel's angular velocity. And so basically what we have is a bullet that goes through this wheel. And so this wheel is going to start to spin, right? It's going to have some final, angular velocity. That's what it is. And we need to figure out what that is. We can't use conservation of linear momentum, because this thing is not going to move. It's going to stay stuck to the wall. And so it's just going to spin in place. and that doesn't have any linear momentum, but it does have angular momentum. So we're going to use that the final angular momentum is going to be equal to the initial angular momentum. So the final angular momentum, we know there's going to be the angular momentum of the wheel and the angular momentum of the bullet, and that's just going to be equal to, let's say, the initial angular momentum of the bullet, or this will be final. Whoops. This will be final. This will be initial. And so to do this, the angular momentum of the wheel isn't that hard to do because we can just use our trusty I omega squared, right? But we can't quite do that for the bullet because it's really hard to define some angular velocity for this bullet. And so what we're going to do instead is use the definition of angular momentum. L is equal to r crossed with the linear momentum vector. So r is the distance here, and then times by the linear momentum vector, which is going to be this one right here. Not, and this is going to have P final. And this one is very similar to how we do torques. Since we're doing a cross product, I go from my axis of rotation, and then my line of action for the final and initial momentum is going to be, I guess it's going to be where that dotted line is already, so I didn't have to draw it. And I go that shortest distance from my axis of rotation to that line, and so I want this distance, which it tells me is 15 centimeters. And so I have this distance here, and that's the distance I'm going to use for r, and I'm going to do r times with p, which is my linear momentum, which is just mv, r times mv. So I have this plus, it's going to be r, or we'll call that distance d, since this is r. We'll say this is r, and this is a distance d. So we'll replace all of those with a d. So this is going to be d, and then we're going to go with d times m final is equal to d times m initial. And my it doesn't tell me what the moment of inertia of the wheel is, but I know from my textbook, since it's a solid disk, it's going to be mr, and this time it is the actual r squared omega squared over 2 plus m final equals d m initial. And then solving for omega is going to give me times m times b final minus b initial. Oh, there's the 2 right here. My masses actually all cancel out, so I can erase. Oh no, they don't, because this is a different mass. That's my bad. Whoops. Mass and radius squared. All of that. I need that. I just need to take the square root. And that is equal to my omega final, or the omega of the wheel. And we'll go ahead and move on. This one I don't think I'm going to do. It has to do with the center of mass. And what happens when we have no external forces acting on the center of mass. It's basically this, the idea behind it. I'll tell you the idea behind the problem, but I'm not going to go out in detail. The idea is that because there's no external forces acting on this canoe, when, and the center mass, I don't know where the center mass is exactly, but let's say it's right here. When these two people of different masses switch places, since there's no external forces acting on this system, the center of mass stays in the same place. And to compensate for that, both the canoe is going to have to move a little bit, and the people, since they shifted around, are going to have moved as well. And so the idea behind this problem is that because there's no external forces acting, this center of mass should be equal to this center of mass if we have the same reference point. So if we define this as our reference point, for example, then the center of mass, this distance right here from our reference point, should be constant even if these two people move around. But we're not going to go through that. No problem. Almost done. We are going to talk about now simple harmonic motion. And so I wrote down a few things here, and I just want to mention some things briefly. Not that. This. Go back. Particularly, I know this looks a little intimidating, but all it's saying is that if we have something times x is equal to the acceleration, that is a condition for harmonic motion. I guess something squared, a negative something squared. That's a condition for harmonic motion. So, for example, a lot of times the primary example for simple harmonic motion is a mass on a spring. So if we have a mass on a spring like this, and it's oscillating back and forth, if I were to write Newton's second law for that spring, I would get negative kx is equal to mass times acceleration, right? Because this is the force exerted on the block by the spring, and this is the mass, or this is just Newton's second law, is mass times acceleration, right? And so with that, this is the second derivative with respect to time. That's what this means. And so if I rearrange it so I get it in this form up here, so if I divide my m over, I get negative k over m times x is equal to a, which is the same, which is in this form, which tells me that this is my omega squared. And so if I want just my omega, all I have to do is take the square root of k over m to get my omega. And that's where this equation comes from. And that's where all these other ones come from as well. But that's just, if you ever, I don't think he'll ever throw anything super complicated at you that you couldn't use these equations for. But in the case that you did have something like that, just know if you get it in the form something times x is equal to acceleration, all you have to do is find what's in front of your x and then take the square root. And that's what your angular frequency will be. Okay, so this one we had in the homework as well. And it's just, I just sort of put this example here so we could quickly go over it and talk about the different parts of the position and the position formulas. And so the standard form for simple harmonic oscillator is going to be we'll use, come on, there we go. We'll use x of t. X of t is equal to the amplitude of motion times the cosine of the angular frequency times time plus the phase angle phi, like that. And so this question is pretty straightforward. We just have to look at the different, I guess this one's different than the one I thought it was. But this is our standard form here. We expect our answer to be like that. We know that's what we have for, and so we need to find each of these constants C1, C2, and C3, right? So if this is our standard form, I'm told that the amplitude is 3.01, so I know that C1 is 3.01 centimeters. And the cosine, and I'm told the period, and this is where we'll use the relation that 2 pi over t is equal to the angular frequency. So if I just do t over 2 pi, so I take this, or 2 pi over t, whoops. If I take this, oh, yeah, that's right. If I take this and divide it by t, then I get that my angular frequency is just going to be 2 pi divided by the period, which is 2.51 times time. And then plus C3, this part is a little harder because we don't really have anything, but we do know that the position at t equals 0 is -2 centimeters. And so to solve for that phase angle, we would just set z of 0 equal to -2 centimeters, and then set that equal to 3.01 centimeters, our amplitude, times, and since t is 0, my omega t is 0, and I just have cosine of phi, like that. And then I can solve that for phi. The other thing I need to worry about, and I don't think you'll have to do anything like that, but it tells us that it's moving towards, so it's starting in its cycle, it's like back here, and it's moving this way. All that tells us is that this phase angle needs to be in a negative angle. That's all it's telling us. And so because it's a little offset is basically what it's saying. It's a little behind. I don't know if you'll ever have to do anything like this on a test, but just in case, I figured I'd include it. And then this one, we'll have to use this one is also a homework problem. We'll have to use we have a simple pendulum with period t equals 2.51 in a location where g is equal to 9.8 meters per second squared. And so it asks for what's the length. Well, if I know that omega is equal to the square root of g over L, is that right? It might be L over G. Let me double check. No, it's G over L. Okay. And I know that 2 pi over, or omega, 2 pi over omega is equal to t. Then if I rewrite that as 2 pi over t equals omega, I can get that 2 pi over t is equal to the square root of g over L. Like that, and then I can solve for L by doing 4 pi squared over t squared equals g over L, and I get L is equal to t squared g over 4 pi squared. That's my final answer. Okay. And that's really all I had for simple harmonic motion. I don't think you'll be tested on anything other than those things. You also want to know to make sure to use, in that case, we're considering a simple pendulum. But if you're given a problem with a physical pendulum, you'll have to use this equation where this is the total mass. This is the distance from the axis of rotation to the center of mass. And this is the moment of inertia of the system. Okay. Other way. Finally, we'll finish up with some of the gravitation and Kepler's laws of planetary motion. Again, I'm not sure if you'll be tested on this, but I will talk about it very briefly here at the end. And actually, we don't really need this either. We can actually do all of the problems that we have in this class using just this Newton's law of gravitation. But if you are going to use Kepler's third law, keep in mind that this A is not the acceleration, it is the semi-major axis of orbit, or the not the aphelion, the perihelion. Which, if it's near circular, you can always just make that the radius of orbit. Just keep that in mind. So next, This one is a problem we had on the last homework of the semester. And it's a binary star system like this, where they have a radius of orbit. They have some speed. We don't know what the radius is, but they have one. They're rotating about their center of mass. They're identical stars, and they have a period t. And so for this one, what I like to do is I'm going to look at just this star here. The only force acting on that star is the force of gravity, which is going to be equal to g. Since the masses are identical, it's m squared over, and this is where most people got tripped up, is this distance. The equation says r squared like this, but that's not the radius. What it's asking for, or what it's telling us to use, is the distance between this star and the other mass. So it's the distance between the two masses. That's what we use there. And in this case, that's going to be 2 times the radius of orbit, which I'll just call r. And that's squared like that. And that's going to be equal to mass times acceleration of this star right here. And so since I know it's a circular orbit, I can approximate this acceleration by saying it's equal to v squared over r. M equals sg m squared over 4r squared. Like that. So I see that one of my masses cancels, this r cancels, and since I'm solving for the mass, this v is not canceled, but it's going to give me that m is equal to v squared times 4r, or not 4r squared, one of my r's canceled, just 4r divided by, g. And that is my answer for that. And then I think for this last part, just wanted to talk very briefly about this potential energy here and what it's useful for. Usually we use it to approximate what the escape velocity would be for an object. And so basically, we're looking for the minimum velocity for an object to escape the Earth's potential energy, essentially. And so when this object is far enough away, we want, this is the potential energy of that object. And this is in not really proper notation, but when this object is far enough away so that the potential energy from Earth is essentially zero, we want also for that object to be at rest. So we want its kinetic energy to be zero, like that. And then initial, so this is what we want its final energy to be, is to be zero, basically. And then our initial kinetic energy is our 1/2 mass times the escape velocity, minus the potential energy, gmm, where m is the mass of, in this case, the Earth, since we're talking about the Earth's escape velocity, over r, where that's just how far away from the Earth it is currently. And so by doing this, we basically get this equation, since our masses are small masses, m will all cancel out. This minus gm over r is equal to 0. Now that m should be gone. And then solving for the escape velocity, we get that v escape is equal to gm over r to 2gm over r. And take the square root like that. And that is, I don't think there's gonna be anything on the test like that, but just in case there is, it works just like we've been doing potential energy in the past, or if we're at some height h, it's mgh. But in this case, instead of using mgh, you're just going to use negative g m m, where m is the mass of the larger object, capital M is the mass of the larger object, and m, lowercase m, is the mass of that smaller object, and then r is the distance between them. And you'll just use that just the same way as you would for another energy problem. But I think that was everything that I had planned. If there are any other questions, though I think there's only one of you here right now, but if there's any other questions, or if there aren't any other questions, I'm going to go ahead and wrap up. And I will post this recording and put other stuff. Maybe I'll go fix. I'm gonna fix. Let's go fix the. Let's go fix. Fix this really quick. See what I messed up on. Not that. Go back. This one. See what I messed up on. See if I can fix that really quick. Let's see. MA is right here. Force on M is mg minus T1. So this would be capital MA minus mg, all right? And that would be negative tension 2 minus mg. So tension 2 is equal to mg plus ma. So that's right. So that did mess up. Tension 1 minus tension 2 is going to be a minus mg. I'm not sure what went wrong here, but maybe I did need to keep it. I think I needed to stick true to my coordinate system and have this be flipped, and that would have fixed it. But anyway, I think that's all. I'll go ahead and stop recording, and good luck on your final.